there's no recording for that class, but I will share a previous recording on it. And I think I need to show myself as well. My lighting is a bit bad today. So anyway, but you can see me now. Okay, so the learning objectives is are the formation of different chemical bonds between atoms, ions, and elements as well. But when I'm talking the atoms or elements, you will be, I mean, you are clever enough to understand that between atoms, they do not form unless they go to some kind of state, and that state we call ions. All right. So predict the type of bonds, what type of bond probably or would they form, what type of bond they are supposed to form if they are in this state, if that atoms or elements are coming from that state, whether there will be ionic bond or polar bond, non-polar bond, metallic bond, or what type of bond. There are different type of bonds that we'll be looking at to it, and these are based on electronegativity, right? However, there is no such term of electropositivity because there is no term. I don't know why, but there is no term. So electronegativity is the only term that we'll be looking at it. And we all you all know that electronegativity is how strongly one atom or element can pull an electron from available electron cloud, how strongly it can pull the electron towards itself, right? So that is the higher the pull or higher the attraction, the higher the electronegativity for them. And then our third objective to learning objective is that the Lewis dot and octet rule, we will be looking at to it. And Lewis dot is a very interesting and innovative. Of course, Lewis is innovative. So it's a very interesting and convenient way of looking at to the electron configuration for different type of atoms. And because of these Lewis dots, it tells us, or it gives us a good idea, a good sense that what type of bond this type of these elements or these atoms are supposed to form. All right. There is, in chemistry, everything is about exception. There are exceptions, but we can have a very good idea of what type of bond it may form if we know the Lewis structure, Lewis dots. And octet rule, of course, octet rule, you know that everyone wants to attain the noble gas structure or inert gas structure, and that is their highest standard, so that they will be very stable. And to get to that status, what do they do? What do they need to do with the electrons, and how do they share or donate or snatch it from others? Apply the concept of formal charge to predict the most likely Lewis structure of a compound. So Lewis structure, another thing is Lewis dots or Lewis structure. Lewis structure also will tell us which is the most stable, which could be the most stable among the different type of arrangement they have. All right, and then again, Lewis dot itself will not tell us what is the most stable connection, but if we know the Lewis structure, then we will be easier for us to predict or to know which of these elements or molecules will be much more stable in that sense. So Lewis structure is very important to know as well, and we will know Lewis structure. Evaluation of chemical bonding theory, I'll go through very fast. There are different type of electron theory. After the atoms were discovered by the Rutherford, that was supposed to be from that, tutorial 2, when the Rutherford came out with this gold foil experiment, people were very interested to know. That's the first time they knew that there is something, very small things inside, and then the particles type. I mean, there are something inside, small, very, very small. So they are called, in an atom, it can be, the atom can be divided. And then people came out with think that, okay, if there are atoms, how do they get to each other? I mean, how do they're holding to each other and then bigger, because atoms are very small, but how they are getting bigger. So the another things came that atoms, different type of atoms, they get associated, they get together and make a lump. Then another question came, how do they get together? Why would they get together? Why not everybody is getting together, right? So there are too many questions came out, and then this is the first of our philosophy, or you can think that, or you can call it the thought that the chemical bonding theory specifically came into an action. People start to think about the bonding, that they are having a kind of bonding that very specific, and it is very useful for the elements or for the atoms to bond to make a molecule. So first of all, in the primary stage, electrons and electrostatic force was the main cause. It was thought that electrons and electronic forces are the main causes that are causing the chemical bonding. And this is true at some point, and it is important, and it also serves our purpose to understand the molecules, the electron and electrostatic force, how they are getting the different type of atoms to do the bonding by transferring the electrons. Okay, electrostatic force. When there is electrostatic force, that means different type of attraction between the electrons or between the atoms they have due to the difference in their valence or whatever. We're coming there later, or electrons charges. So when there are different type of attraction between the electrons, the electron will be transferred, and then ionic bonds are being made. But it does not give us the idea. I mean, we can explain the sodium chloride, potassium chloride, that type of ionic bonding. But what about hydrogen? What about chlorine? That is diatomic gases, nitrogen, oxygen. It does not solve this problem. So there comes the sharing of electron. That not only they transfer the electron, they also share the electron between them, among them, to become stable. So valence shell and octet rule came. Lewis came out with this idea that, okay, since they are not just taking one and then one is just giving, there is something that is association, there cooperation between them. That means sharing. Sharing is caring, yeah? So they are sharing as well, the electrons between them, the valence shell electron, and that is how the covalent bond are being made. But there's another type of bonding, that is valence bond theory and molecular orbital theory. It came between to explain more about the different type of bonding that occurs. It is based on quantum mechanics. And they have different type of rules of, the electron state, electron energy state, different rules. It will not be discussed here, but it will be your job to, sorry for this. It will be your job to go through this different type of bonding, and then it will be useful, or you have to put it in your assignment later on. Okay, but I'm here. If you have any question, I am okay to discuss it. If you have some question, or if you need more clarification, I'm okay to discuss about this valence bond theory or molecular orbital theory. We'll just give a very simple, a very brief introduction about these things, so that if you want to search by yourself, you can do that. Interatomic bonding. Ionic bonding, the electrostatic force between positively charged and negative charge are higher, of course, because positive and negative charge. So when the charge attraction is considerably higher, not all the positive and all the negative, because they are not 100% positive, 100% negative, they are delta positive, delta negative charge. That means slightly positive, slightly negative, depends on their position in the periodic table, and on different type of atoms as well. So when the charges are very much different, or very much strong, or what do you call it, the attraction are very much strong, so they will form an ionic bonding. And since ionic bonding is by exchanging of electron and static, based on the different type of electrostatic forces, we usually perceive that it's a very strong bonding, and it is strong bonding. But not all the hard materials or strong materials are based on this ionic bonding as well. metallic bonding is metals are metallic bonding, and they are very strong as well. Covalent bonding between the negatively charged and positively charged ions is not very hard. I mean, is strong, and they share the electrons between them. All right. So when they tend to share the electrons, the valence electron between them, two of the atoms together, they form the covalent bonding. And this type of covalent bonding, in fact, they have, based on their electrostatic forces, the difference, although they are sharing, not just snatching away from one another, they are sharing, but still they do possess that the difference in electrostatic forces of the electrons or the atoms they generate. So if the charges are very different from one atom to another atom, or even though they're covalent, there can be ionic covalent or non-ionic covalent. If the charges difference is very strong or very high, they are covalent, but still ionic covalent they can form. We'll go much detail into it later. Metallic bonding. When the electrostatic attraction between positive charge metal ions and the negative charge metal ions from the sea of electrons, they have the, of course, they have the attraction, electrostatic attraction. If there is no electrostatic attraction, there is no bonding. So all three of these type of bonding, they depends on this electrostatic attraction, but different type of attraction. If too strong, moderate is strong, or if there is a strong, but if based on the availability of the electron. So there are graphics for this metallic bonding. All right, for the is coming from the next slide. But the metallic bonding, when the atoms are there, it is having the attraction force. But this attraction force, they are taking the electron from the sea of electron. The electrons are all around these atoms, and it is very available. So it can just take one, or it does not need to keep that one. It takes that electron, and if it is removed, there is available another electron that it can take it. So there is the abundantly available electrons all around that atom, and that is how they form the metallic bond. And that is why metals, they form the metallic bonding. I mean, they are very much conductive of electricity or heat. Here is the covalent bond. They are sharing that electron, two atoms, each of them. For example, it's the hydrogen atom. We understand that it's the hydrogen atom. Each of them has one neutron and one electron in it, and one proton and one electron in it. There is no neutron in hydrogen. So one proton and one electron, and they are not stable. Can anybody tell me why they are not stable? It is your main. Let's say it is a question, Menti question. Why are this hydrogen atom by itself are not stable? Why are they not stable? Anybody want to guess? Just a quick answer, maybe. No? Simple thing. That they haven't attained the helium structure. Helium needs 2 electrons, right? Helium needs 2 electrons so that they will be very stable in that outer shell, at least for outer shell. So to get that structure, helium structure, these atoms, they do not have enough power to snatch one electron from others, right? So what they will do is, when you cannot fight with your enemy, what is the best option that you do? You cooperate with them, right? You make friends with them. So I don't know whether it's a good example, but it's off the record, yeah. So yeah. Say they do not have enough energy to take the one electron away, snatch away from others, so they will just cooperate each other, and then there will be 2 electrons and 2 protons together in that atom. Consider that it is the same atom. Consider now this is the same atom, one atom, right? And these 2 protons are coming very close to each other. So in this way, they are forming a helium structure. In this way, they are forming a helium structure, and that is very good. So they're very stable in that way. Ionic bonding, however, is the different way. This one, let's say this is chlorine. Why it is happening this way? Okay, let's say this is chlorine, and this is sodium. This is sodium and this is chlorine. Both of them, chlorine has the potential to snatch 1 electron away, right? And then sodium has the ability to shed 1 electron, and they need both of them. Sodium needs it to get to that 10 electrons so that it will become neon structure. Chlorine needs 1 more electron so that it can become argon structure. So that is why chlorine will take by force 1 electron away from it. Sodium is leaving that electron and giving it to them. All right. So what is happening is transfer of electrons. So you can say that, okay, once sodium become shedding that electron and it becomes a neon structure, why don't it just go away? It can enjoy itself. It becomes now positive. I mean, helium structure. It can no, but the problem is why? Because it still has this many of proton inside, that still has 11 proton inside. So 11 proton are supposed to be neutralized by, or the 11 electrons charges, or 11 stacked attraction. When it is released 1 electron and give 1 electron away, it becomes positively charged. That means the proton charge, the nucleus charge become higher, and it is positively charged. Chlorine took 1, it become negatively charged. So although sodium now, after shedding 1 electron, becomes stable, our neon structure, still it has the new problem on his head, that is positively charged. And it cannot go alone and stay as positive. So it has to attach to a negative one so that it can neutralize, the positive charge can be neutralized to some extent, at least when they are together. So that is why they are staying together as a molecule, not an atom. They are different atoms staying together as a molecule, and now they form sodium and chloride. Same goes for other ionic structure as well. Sodium chloride, potassium chloride, barium chloride, calcium chloride, all those things, the same way it forms. But this structure, okay, ionic bonding and all these things, covalent bonding, does not always give us the, it does not always explain the things that it will, how all this type of bonding will be occur. Some of the bondings cannot be explained. And the stability of the atoms, they are also not stable, because in a molecule, the atoms, they are not in this very simple way that different balls are just coming together and then attaching each other on the flat surface. Not like that. They stack up one with everywhere, 3-dimensional way, right? They stack up to one, I mean, layer by layer as well, side by side as well. So that is why we need to understand that how or why are they stacking up? Why are not that only one plain surface? Why are they are not forming the one sheet, like one plain sheet on the same surface? Not like that. Why they are having bulky volume? So G. N. Lewis, he started to investigate on it and try to understand that how do this actually, atoms, they form, or molecules, they are formed. This is Jean Louis, he's working in the lab, and he innovated a good way. All different, I mean, every single atom, he started to prepare it as a 6 box, okay, as a box which has 8 different type of plane, right? It has 8 planes. So this is one, this is one, this is 1, 3, 4, 5, and 6. So 6 plane and 8 corner. It has 8, all of them has 8 corner. He started to think in that way. And then he put the valence electron to each corner, because if the 8 corner is filled up, that means it is very stable, right? 8 corner filled up means very stable, and it has its octet is filled up. And if it is not, that means it's unstable, and it can be the other corner should be filled up with electrons. So this is his idea, and his idea was he's worked out, and it was very okay. I mean, it was quite helpful later on for us to understand how different type of molecules or atoms form bonding with different type of atoms to form molecules. Ionization energy. Why do we need to consider ionization energy? Anybody wants to guess? Chain when weak attraction force. Why did you, I mean, what was the question that I asked that you replied? That's why you, in real time, you can just unmute yourself and weak attraction force. It doesn't take long, right? Okay, so I forgot actually, but thank you for your answer or for your reply. I forgot what I asked. Anyway, so my question is, how does this ionization energy is helping us to understand the different formation or the formation of molecules? How does it help us? Ionization energy. Ionization of energy is the amount, no, why I'm making. See. Okay, ionization of energy. All right. So for ionization energy is just opposite to the electronegativity. All right, it's just opposite to electronegativity. It's just electronegativity is the way or the attraction each of the atom is having to pull one electron towards itself, right? So in that case, fluorine has the highest, and it will attract more electron towards it. Doesn't matter from where. All right, it will try to attract more electron towards it, so that it has a higher attraction force. But for ionization energy, it is the opposite thing. Is how much energy do we need to take one single electron from the outer shell, of that atom. So for helium is the highest one we see. It is the nucleus, it has 2 electrons. If you want to take one electron away from it, this is electron. If you want to take away one electron from the outer side, I don't know why it is happening this mark. I'm not doing it, but it is all automatically happening. So if we want to take one electron from outer shell of this helium, we will have to exert 2372 kilojoule per 1 mole, and it's a huge number. It's a very strong force. I mean, energy is a very strong energy. So this much energy you need to exert to get one electron out. That means helium does not want to release one electron. And helium also does not want to take one electron. It is very stable. Of course, they are noble gas. Neon is the second one. It does not want to give more electrons. And then you see that it is coming down in this way. And hydrogen is there, and also it is going up in this way as well. Right? There is some, of course, a difference for taking electron or giving electron. For oxygen is lower than fluorine, and oxygen was supposed to be here. Oxygen was supposed to be here, but oxygen is lower because oxygen, due to the structure, right, it is easy that it can donate 2 electrons, right? So that 1 electron is okay. So second electron, if we want to take the second electron, it is almost impossible from helium or neon or hydrogen. Hydrogen does not have 2 electrons anyway. For fluorine, from fluorine, but for oxygen, it is good to give 1 electron because it knows that if it gives 2 electrons, it will get to the neon structure. It will jump to the neon structure, right? So that is why oxygen is at least okay to give 1 electron, so that it is what do you call it? Ionization energy. Now, for oxygen, what I was showing that oxygen has 8 protons in nucleus, and nitrogen has 7. Both of them are having the similar type of size. Fluorine, oxygen, similar type of size. But since 8 electrons are here altogether, the shielding of oxygen, the electrons for these 8 electrons is higher. So that at least we can take 1 electron from here more. But for nitrogen, it has 7 electrons, so the shielding is a bit less compared to the size of oxygen to nitrogen. Size is almost similar, so that nitrogen is less shielded because of 7 electrons. I'm sorry, 7 protons. And around it 7 electrons. So it's less shielded than oxygen. So that is why oxygen is highly shielded, and it is okay to, easier to take 1 electron from here. But you may say that, okay, why not for fluorine? Fluorine is now 9 protons in it, and it knows that rather than giving electron, if we take 1 electron, it will attain to neon. So that is why it is very hard to take 1 electron from oxygen as well. So the ionization energy for oxygen is very high as well. So that, this table is telling us that which of them atoms or elements will form a positive charge, right? Which of them will form positive charge and which of them will form negative charge. So can anybody from here today tell me which of them will form a positive charge on this that you can see from the slide? Which of the elements, you can just tell me is left, right, up and down or something like that. It's okay, don't have to be specifically period or groups or anything. Just tell me which side it will be easier to form positive charge. Left, good. So Chewen Kong, Lentia, Audrey, thank you very much. Left will be easier to form positive charge. Why? Other than these 3, anybody wants to reply? Iman? I have a bad habit to call people name. Jonathan? Keshwan? Anybody? Why is it that it is okay for them to form a positive charge, the left and the side elements? Ramat? Sean? Gabri. Because it is okay, it's easier to take electrons away from them. You see that sodium is 496. Okay, let me. Pointer option. Let me delete it. So you see that sodium is just 900 and 419, 96. Potassium is even lower. Cesium is even lower. If there was francium, it would be much higher, lower than this. So that is why they easily form positive charge. They are forming positive charge easily. Of course, this is much easiest, and hydrogen is not that easy. So you can think that water, you want to break the water to hydrogen gas, it is not that easy. You need a lot of energy. All right, okay, so now we go to this electronegativity series. Ionization and electronegativity both are helpful to understand what type of bonding it will form. So as we discussed in previous slide, that electronegativity, it goes from this end to this higher, diagonally, from left bottom to right bottom. And it also goes from bottom to up, higher, everywhere. All the groups, it will be in this way. I think my system is a bit problematic. So no matter where you are looking at for a period, you will look through this. For a group, across the group, you go from bottom to up. It will the electronegativity is increasing. You are going from left to right corner, left bottom to right top. The electronegativity is also increasing. We discussed about it last time. Can anybody tell me why? Anybody want to try? There is no point, though, no marks on it. So you can just try. It is okay if we make mistakes. If we don't make mistake, how do you learn? Right? Electronegativity is how much they want to attract the electrons, because they do not want to attract the electron, they just want to shade the electrons so that they can go to previous, like helium here, right? It's helium, it's neon, this is argon, and then krypton. So helium, is He. If so, lithium just shed one electron, it is easy for it to go become a, helium. If sodium shed one electron, it is easier for it to go and become, neon structure, and so on. And that is why it's easy. And when we come to the transition metal, of course, they will be easier for them to donate electrons, because the metal, they have metallic character, so they are donating the electrons. That is okay. We have talked about it. Now, Lewis dot symbol. As we mentioned previously when we saw the Lewis photo, that for Lewis, dot symbol, the valence electron, only the valence electron will be shown around it. And it is important for us. It is important for us to understand the Lewis dot symbol, so that we will be able to we'll be able to find out the Lewis dot structure, or for an element, for a molecule, and bond formation of the bond. The number of unpaired electrons in an element can be used to predict the number of bonds that an element will form in a compound. So only the unpaired electrons, one electron will form one bond, although in a bond we need two electrons at least. So one electron, unpaired electron, from this element will go to form another. Okay, it will be easier when we go to this example, but we always will not put the example. You have to imagine yourself the examples. There are so many things to give to examples, and also I don't want to give too many examples to limit your imagination, so that you can imagine. And the more that you have the ability to imagine, the better you visualization you will have. So hydrogen, let's start from the hydrogen. Hydrogen has only one electron. So for Lewis dot structure symbol, we just put one dot. One, it is representing one electron. Helium has already two. So it's two electron at the outer shell, only on the outer shell. That is the inner shell, IS2. Oh, sorry, 1s2, 2s2, 2p6. Doesn't matter how many orbitals it has. We are only considering the outermost orbital. Lithium, sodium, potassium, rubidium, cesium, francium, all of them has one electron each at the outer shell. For alkali earth metal, this is alkali metal, right? We know this one, and this is alkali earth metal. Beryllium, magnesium, calcium, strontium, beryllium, and then barium, and then radium. All of them has two electrons at the outermost shell. So it goes in that way, same. Aluminium, silicon, phosphorus, argon. So this is how we will be representing all the elements all through this periodic, the chart on the table, so that it's easier for us to understand what type of bonding or how many bonds they will form. For example, why I'm saying that how many bonds they will form. Boron, it has 3. So it can form 3 bonds. It can form, usually, we will see that boron is very interesting character. So it can form 3 bonds. And these 3 bonds that will not make it stable. It's not a good example to start with, because we will see later on boron is a bit different. Okay, for carbon, it has 4 electrons all around it. So to get to that 8 electron, it needs another 4 electrons, right? So another 4 electron will make 4 bonds in carbon. Another 4 electrons will make 4 bonds in the carbon, and then each bond is having 2 electrons, right? Each bond is having 2 electrons at the end. So when we make one bond in this way, that we automatically understand there are 2 bonds. 2 electrons in one bond. When we say double bond, that means, let's say A has double bond. That means A is sharing 2 electrons, and X, see, X is also sharing 2 electrons. So these 2 electrons is coming from X, 2 electrons coming from A. So these 2 electrons and 4 electrons, A and X both are having 4 electrons between them, but 2 bonds. So each bond there will be 2 electrons. And here for nitrogen, there is 1 pair already here. For oxygen, there is 1 pair or 2 pairs already, right? For fluorine, there are 3 pairs. So these pairs, they are not making any bonding. These pairs, they are not making any bonding. Only the lone pairs, 1, 1, 1. So this nitrogen will form 3 bonds. And there is already 1 pair, so 8 electrons. Oxygen will form 2 bonds or 1 double bond. Fluorine, however, only one bond. Fluorine cannot have two bonds. Sometimes students write fluorine is having two bonds like this. Double bond to chlorine. It is a very big zero if anybody does so. So I hope that is okay for us to understand that how bonds are being made. Octet rule tendency to form the, as I was telling that everyone try to form the octet. Everyone's try to want to be a billionaire, so that the octet is the billionaire capability, right? So this is the billionaire club. Let's say in that way, everything is money now. So important money, since that this is the highest number billion. Everybody wants to be there. And that is why they will either share the electron or take electron, fill up the octet and become the octet rule will be formed. Octet rule only involves s and p orbitals. D orbitals are not filled up, and that is why these transition elements we have not shown. It is almost impossible for the d orbital because it has so many valence electrons. We have seen for this transition element that they have variable valencies, right? Some of them forms positive 2, positive 3, positive 4, positive 5. One single element can form different type of positive charges. That means they have variable of variable valencies, and octet rule does not explain them. So Lewis dot symbol is not good enough for them to explain their characteristic. And that is why only one type of theory in chemistry does not work for all. And that is why, anyway, don't talk much. So octet rule only involves s and p orbitals, right? It's not everything. Ionic bonding, electrostatic force, negative charge and positive charge, they will form electrostatic force and then lose up the electrons. Somebody will gain, somebody will lose, and then that is how they will do the association and form the bonding. Example of ionic bond, lithium fluoride, the very basic example. At the beginning of the periodic table, lithium and fluorine together. So as we know, you also have rightly predicted that left side will form positive charge, right side elements will form negatively charged. So left side animal has positive charge, that means they will shed electrons, and right side elements, they will gain electrons. So in the same period, right? So lithium and fluorine are making a bonding. Lithium is giving the electron and fluorine is taking that electrons. So we see that first ionization energy is positive 420 kilojoule per mole, right? 420 kilojoule per mole. And first affinity, electron affinity is negative 320 kilojoule per mole for fluorine. So lithium and fluorine is coming together. They are readily forming the lithium fluoride. Can anybody tell me? All right. Can anybody tell me what is the implication? Not implication. What does it mean? What does it mean by showing that 420 and 380, 300 negative 328 kilojoule per mole? What do you understand about it? Is it easy to form or is it hard to form? And if it is easy, why it is easy or so? Anybody wants to reply, please? Hello, anyone? Is it will this reaction occur automatically or not? Easy. Ainin says easy. Oh, it's the note of interrogation. So how many of you have taken the thermodynamics class? Already finished, or you have taken just this semester? So if it is we don't have time. So if you if you are in the thermodynamics class, you will see that the energy difference in energy. First ionization energy is 420 kilojoule per mole. All right. So that means we need to provide 420 kilojoule, but for electron affinity for fluorine is negative 328. So there is a difference of how much is the positive. So that we have to provide some energy for it to do the bonding. All right. So here we see that sodium and chloride, the energetics for ionic bond formation. We can consider lithium chloride as well, but sodium chloride, the graphic is available from the book, so it is we have taken it. I have taken it this way. So sodium and chloride. Chlorine is bigger atom. Of course, it's bigger atom because it has more electrons. Sodium is small. That is why it's showing. When they are very, this is R is the, distance between the atoms. So this is one atom, let's say this is another atom, and this is the nucleus, the center. This is one difference. This is a radius, this is another radius. So when they are together, attaching, the distance between them is the R. Right? So the R should not be less than their radius. This is R1, this is R2. This is R. If the R is less than the radius, their respective radius, they will have a very much repulsive attraction. They do not have enough space to, to comfort themselves, make comfortable. And that is why the potential energy will go very high, and then there will not be any formation of bond. And if the R is too far away, that means they do not have any possible bonding between them. And the distance will be too far away that they do not form even a bonding. That is why. So R is 0 here. That means the potential energy is 0. But that is not enough for them to make the bonding. When the R is at 236 nanometer, it is in nanometer scale, I believe. So when there is a 236 nanometer, so that the potential energy is low. The lower the potential energy, the higher the stability of them. All right. And yeah, and then when they are going away, far away from the R or from each other, this is R is 600. That means they have moved away from one another very far, and they are not having any attraction between them, these two. This is the perfect one. This is too close. So it cannot go very close. It cannot go very far. All right, go to Menti faster. Go to Menti faster. I have a question for another 3 minutes. We can finish 4 minutes. In fact, I have. So go to menti.com and put this code number of 7924 79242812. Faster, do it. Voting is closed. Okay, voting is open now. Do it. Another 3 minutes, but I will give you only 2 minutes to finish it. Faster. Okay, I'm setting the time now. 1 minute to go. Nitrogen, oxygen, chlorine, HCl. Which one would take higher energy to break? You have to provide much more higher energy. Which one? So that it will be broken. Only 6 of us has replied. 30 seconds. 30 seconds. Faster. Faster. 20 seconds. Don't worry, I do not know who is voting for what. I just see the number. I cannot see who is voting for what option. 8 seconds. 7, 6, 5, 4, 3, 2, 1. Okay, voting closed. So I have 4 to 8, 10, 11. Another 2 students who are here but not listening. Next time I'll start doing the roll calling, yeah. So it is not for the sake of just attendance, for the sake of learning and engagement. So 4 to 6, 8, and 9 students have voted. 4 has not, haven't. I do not know who is what, but I will discuss about it, which one is correct and why it is not correct. I'll talk about it next tutorial or next class first, and then the tutorial. So yeah, all the best. Take care. Have a nice day and enjoy the rest of the day. Okay. Okay. Thank you. Bye bye. Take care.